Good morning. Okay, I'm still gonna wait maybe one more minute before starting. Just this seems like a few less people than we normally have. If I put that into full screen, does everybody see it or are you? Okay, cool.
That looks great.
Awesome. Well then I will get started. Um, so welcome everybody back to AI Summer. Happy Monday. So if you were with us last time on Friday, you saw me talk all about reinforcement learning and including showing a notebook where we were training a model with reinforcement learning. And we mentioned many times in that notebook that the training will take a very, very long time because we weren't sort of implementing any of the methods that I'm going to talk about today to sort of speed up fine tuning. So even though we chose a pretty small model, we were sitting there and waiting for kind of this full fine tuning pipeline to happen. And I hinted at many times during that there are totally techniques that we can implement to speed up fine tuning very drastically. And so this sort of suite of techniques is called parameter efficient fine tuning. And so hopefully today we'll talk about that. We'll go through it in code and you will see that, like so many other things in machine learning, Hugging Face in particular has put together a wonderful PEFT library for us. That means that actually implementing this is super easy, and you can implement this really easily on top of just any existing model you're going to train. All of the methods we're going to talk about today are pretty much that easy to just stick on top of the existing training of a model you're going to do, and you can get this blazing fast fine tuning without too much effort. So probably the stage is already set, as I said, sort of based on what we saw with the notebook on Friday. But just to sort of recap, maybe when you traditionally think about training a model, you're probably thinking about one of two things, where the first is training from scratch. So this would be like full training a model, like you begin everything is randomized. It has to fully learn all of the data that you have. But maybe another sort of thing that you could think about is doing fine tuning. So again, this is sort of very standard way of training a model where you simply start with the existing weights, you keep training it on new data, but it's basically the same thing as training from scratch. It's just that you're starting with some weights that have already learned something. And so you're not starting from the beginning, but the process is sort of similar. Parameter efficient fine tuning is a particular sort of uh, edit to how you sort of do this whole thing. So you start with an existing model that has weights, but you're freezing basically the whole entire underlying model. And you're training a much smaller set of new weights. And I actually think that in the next slide, I'm going to change that word weights to parameters, which is more accurate. It's not necessarily weights that you're training. Sometimes it's just kind of these additional parameters. But the idea is that most of the model you can actually kind of hold frozen and just insert very strategically some subset, some smaller space of parameters and train just those. And that's enough to guide your model to a different behavior, different domain, new set of adaptations without really changing much of the underlying model at all. So of course, that means way less compute needed, right? Especially these two things on a full set of, it's a 30 billion parameter model. That's a lot of compute. Freezing the 30 billion parameters and adding a small set, that's way less compute. And there's also much fewer model adaptations happening, which might sound like a bad thing. Like, oh, I have this brand new task I want to, you know, adapt my model to. So not a lot of model adaptation might sound like a bad thing. But truly, a lot of what these models understand is not going to be necessary to be changed for adapting to any small task. So the idea here is actually few model adaptations is very beneficial. You get to keep a lot of the existing behavior of the model. You don't risk changing it at all because that's all frozen. You're just adding a little bit of tweaks that you need for a specific thing that you want. And so parameter efficient fine tuning, I already said a lot of this, but just to kind of summarize these points, basically the point is you're fine tuning much less of the model. Typically in like a lot of parameter efficient fine tuning methods, um, they end up giving you like a percent, like, we train X% of the model. And the idea here is that this is, however many new parameters you added that has to be trained, just that fraction over the total size of the model is what that percent is. And it ends up usually for every PEFT method being very small. I would say like under 3 to 5% of the total size of that total 30 billion parameters is what typically ends up being trained kind of across all of the different PEFT methods. And again, sort of the core idea here is that a large model typically has maybe more parameters than it needs, or most of the parameters are not needed for any given specific task. So if you've trained a model to like understand how to put together sentences, right? Like a lot of that does not need to be changed when you want to like tweak the model to now give a medical diagnosis instead of a literature review. Its fundamental understanding of how language works and how sentence structure is, its vocabulary, like all of those things exist somewhere in that huge number of parameters, but don't need to be edited in order to adapt to a new task. So the changes that any new task needs do exist in this much smaller, lower dimensional subspace. So you could take advantage of training just a much smaller, lower dimensional subspace to adapt to it. And then another just very interesting thing that we'll see, and that's a very cool thing about parameter efficient fine tuning, is that a lot of the methods, most of the methods are pretty modular. So because the model ends up being frozen and we sort of add new weights on top of it in most PEF methods, that means that you can simply remove the additional parts and return yourself to the base model of all of the frozen weights that you started with. And that's a really great feature because it means that if you have some set of PEFT weights, parameters that you trained for a specific task, you can very modularly add them or remove them as you want. And your base model doesn't have to ever change. So you can have one base model and you tack on your medical diagnosis weights, and then you remove them and tack on instead your literature review set of parameters, and the underlying model doesn't have to change. You don't need 5 different versions of this gigantic model. You have 5 different versions of some very small set of task-specific weights instead. And that is very advantageous, again, when you're trying to sort of work around just the sheer memory that some of these models are going to require you to have. Okay. So we're going to talk about, there are a lot of different PEFT methods. I'm going to talk about 3 particular overarching methods, and then within those, there's lots of different flavors of each of these. Um, Prompt/prefix tuning and adapters. we'll sort of touch on the notebook that I'm going to walk you through today, is going to be all about this third method, which I believe it is my understanding is sort of by far the most popular PEFT method. So we're going to focus on that mostly, but I will touch on these other two kind of before we get there. So the first method that I want to talk to you about is prompt/prefix tuning. So again, in every PEF method, we're just finding some very small set of parameters that we can do our training on instead of the full size of the model. And so the idea behind both of these methods that are kind of similar is that you train this thing called a virtual token. And it's a small set of now learned vectors that are able to steer the model to a desired behavior. And virtual tokens is a way of saying they're like trainable vectors that are gonna act like tokens, but they aren't, and they do not need to exist literally inside of the vocabulary. So this is a method where we're not going to update the weights. You'll see in other PEF methods that we'll talk about today, like the weights themselves will get some sort of small update. This is like a small representation vector that just gets stuck onto the way that the model is understanding the current representation of the information and then learning a tweak to that. So maybe if we lay out these things a little bit more, that'll make sense if it's sort of not feeling super intuitive. The two sort of main methods, prompt and prefix tuning, are basically just vectors that you're inserting into different places in the model. So in soft prompt tuning, it's a little vector that you're inserting into the input embedding sequence. You can think about it like a set of instructions, but that doesn't actually have to like exist of words. It's like both of these methods are sort of like hidden context for the model. So you're tweaking how the model understands what you told it, the real like input prompt. But you're doing it in a way that is learnable to the model and that doesn't have to map to you like putting in literal instructions. So you don't have to formulate, in words what you want. It's going to learn how to sort of change its representation in its internal hidden space, its understanding of what you want and what you've told it. It's going to learn how to tweak that for the specific stuff that you want. And so in soft prompt tuning, that's into the input. In prefix tuning, it's into the literal attention mechanism of the layers. But in both cases, the fundamental idea is that you're not editing weights here. You're editing more where its understanding in the hidden space exists. And so, like I said, I think really the idea of maybe like a hidden context is the best way to understand these methods. It's like you're adding additional context that you didn't have to actually define, learnable extra context directly into the model itself. Okay, that's all I'm going to say about those. I think it's cool to know about, but again, we're not touching on it today. So just to sort of give you a brief explanation of that. The next one that I'm also going to give you a pretty brief explanation of are adapters. So adapters are basically, I think the way to think about them is sort of like mini layers that can get stuck into certain parts of the model. So a mini layer, think about just like a normal layer of a model, but it has very few weights. And so you just sort of insert them, and I'm not being specific about where you insert them because there's lots of different ways of inserting adapters. So depending on, what paper came out about what adapter technique, they're inserting it in all sorts of different places. But the idea is that if you just insert a couple mini layers, you freeze the rest of the model. The mini layers have some sets of weights and parameters that you train those, and everything else stays frozen. And again, big thing here is that they're lightweight, modular. You can swap out different adapters very easily because they're not changing the dimensions of the model. And so they can just be removed and you don't kind of like lose anything in doing that. So in a standard, this is probably the, I think, most popular kind of way of inserting adapters. Um, and so in a standard layer of a transformer, you might have an attention layer that's followed by feed forward. And so this is a very standard sort of transformer layer. And both of those would have, let's say, some size D, the size of the model. So we need to preserve the overall size as we pass things through a model. Otherwise, they don't understand how to operate on each other and it causes a problem. So a common place to insert adapters is just you insert one adapter after the attention mechanism and another adapter after the feed forward. And the idea here is that these are very small layers that start with your same base dimension, shrink it down to some R that is much, much, much smaller, and then re-increase it up to size D. So this little layer just shrinks and re-increases whatever comes into it. But in that operation has a bunch of learnable parameters. But because we've just kind of shrunk and resized the same information, we could pop that adapter back out. We haven't really fundamentally changed anything about the model. We just like stick them in and stick them out as we want. And as I said, that's one particular flavor, this first one, where you are sticking them specifically after attention and feed forward. But there are lots of different adapter methods that get inserted into different places in the model. And so I've sort of put this table, I will put these slides on the GitHub, and this table is just kind of for reference about all of the different ways that these adapters are commonly inserted, but we're not going to go into detail about all of these different methods. But again, each just sort of has their own flavor, number of parameters that you are changing, so different amounts of sort of tuning that each of these would take. So the one that I was talking about where this Holsby, that's sort of a lot of layers. Like this one is shown to perform really well, but it's sort of a lot inserting all of these little mini layers like after every single attention and feed forward. So some of these other flavors are just trying to be much more lightweight, get away with inserting much fewer layers and still try to get sort of the same performance. So that's largely kind of the difference between all these methods, but all of them are basically inserting one of these layers somewhere. And then just to sort of highlight again, because we're not going to talk about it today, but these slides will be available on the GitHub, just exactly like how easy it is to implement some of these things. So of course there is an adapters library. And so it's as simple as taking your model and adding an adapter to your model, and then you just do your normal training. And this adapter library will sort of take care of how exactly to insert the adapter layers based on the sort of configuration that you told that you want, and then handle the training of them and all of that. So just to sort of emphasize that for all of these methods, these libraries exist that make it very easy to implement and to choose one of these and be able to go forward and test it very quickly. Okay. But the final flavor that we'll talk about, and the one that, again, the notebook that we're going to talk about today is actually going to cover, is this idea of low-rank adaptation. So LoRA is sort of the standard. As with the other PEFT methods, there are a lot of different particular flavors of this, but that sort of all build on this same underlying concept. And so the idea behind a low rank adaptation, this is a version where we're more sort of directly thinking about manipulating the weight matrix itself. So obviously any model has many, many, many weight matrices, and this is sort of applicable to any and every weight matrix that exists in the model. So we're going to focus in on like what a particular weight update would look like, but this would hold true for whatever weights in the whole model you want to apply it to. So the idea is that instead of updating a whole weight matrix, which is sort of the typical full fine-tuning thing to do, you add just a small small weight matrices that update the weights in a way, but the two smaller weight matrices are much smaller and they are made of trainable parameters, but because they're so much smaller, they take much less compute. And so I will show you exactly what that sort of looks like. Um, Sorry, I'm reading a question. I'll show you exactly what that looks like, hopefully, in the next slide. When I say something like size of the adapter must be the same size as the model, could explain a bit what that means. Yeah, so let me go back to so the idea here is that given um, for any given layer, information is coming out with particular dimensions. And the particular dimensions, because it's always just a bunch of matrix multiplies, the particular dimensions have to match or the matrix multiplies don't work. So when something comes out of our attention layer with a dimension D, it like fundamentally cannot go into the feed forward layer if it doesn't still have dimension D. So any adapter layer is going to ultimately have to give information out also at size D and take information in at size D because it's coming out of here at size D and it has to go in here at size D. So typically what these adapter layers do is sort of bottleneck the information. So they take it from size D to size R. So that's a really small matrix that takes your information from size D to R. And then another similarly small matrix that can take it from size R back to size D, as long as that R is something that's really small. And so that's the idea behind the sizes of adapters is that they're very small in their number of weights because you do this bottlenecking thing that really shrinks the information down to this really small size R. But you reblow it up then later um, so that you pass it forward. But in this shrinking and reopening, you can kind of get away with having very few parameters because you've sort of temporarily shrunk the information. So does that make sense? And yes, when you use the adapter library, it knows the sizes that come out of every layer. And so it will say, you'll choose a size R that you want, but that D, it is fixed by the model. And so it's going to say, okay, I know coming out of this, this is size D, then it'll fix this to do this D to R to D based on the R you've chosen, but the D is fixed and it knows all about that. So yeah, it's handling all of that for you. Cool. Okay. Yeah, and actually it's a very timely question because LoRA is going to do a lot of the same sort of thing with this like rank matrix crunching information and then resizing it. So we're about to sort of see the same thing in LoRA, but LoRA is doing it at a weight matrix level, not at a whole like layer level. Okay. Yeah, so with low rank adaptations, we're going to do actually basically the same thing that we just talked about, but on a weight matrix level. And the idea being again that same thing with the adapters where, you know, these small layers have very few parameters, these small matrices have very few parameters, and so they're quick to train. And again, like I said, all of PEFT methods, not all of them, but for almost every PEFT method, it's true that because the original weight matrices get to remain frozen, these can easily be sort of added and removed. Okay, so at sort of a weight level, this is a, extremely simple example of what maybe like one pass in a feed forward network looks like. If you have taken, you might remember from like basic neural network class, or just if you've ever seen how people draw a basic neural network, this is a very common way people draw them. But the idea is that you have some weight matrix that is operating on the output from some layer, and that gives you a new size input. And models have tons and tons and tons of these weight matrices that just operate to take information, multiply it, and output information of a particular size. And the weight matrices tend to be very, very large, right? In this example, it's like a tiny thing, but they tend to be absolutely gigantic. The idea behind LoRA is that if you add weight updates to this weight matrix, but that are in the form of two really small matrices that when they multiply together do have the same size as W, but independently, so sorry, calling this W, um, but independently are very, very small and have very few parameters, then the number of parameters you have to update between B and A is super small, but you get to sort of update all of the weights of W. And so if you remember matrix multiplication, if you multiply, okay, in this particular example, this weight matrix isn't square, but they usually are. So I guess assume that D is like, imagine a weight matrix that was square and has D and D sizes for the way that I've written this. If you remember matrix multiplication, when you multiply a matrix of size D by R by a matrix of size R by D, you basically can drop the inner dimensions and keep the outer, and that will be the size of your final matrix. So even though both of these are really small, again, we choose an R to be really small. So if D is 1,000, but R is like 4, and then the same here, it's a 4 by 1,000, that's way fewer parameters than if both of these things were 1,000 by 1,000, right? So we choose a super small R such that each matrix itself doesn't have many parameters, but the size of them when multiplied still works out to be able to just straightforwardly add to our weight matrix and do updates to our weight matrix that way. And so again, we're preserving all the original sizes of the model. We don't have to change anything. We can drop these out. And because they just edit this slightly, like we haven't changed anything about any of the model architecture, but both of these matrices separately are super small, so we can run full, back propagation on them, and it doesn't take that much compute to update them very specifically to learn how to edit this slightly for a specific task. And in LoRA, you can do this so again, this is a very simple representation of some particular weight matrix in a simple layer. But this can be done for every weight matrix in the whole model. And again, choosing that R small enough means that, even if the D is large, if that R is small, adding this to every single weight matrix in the entire model still only updates like a few percent of the total parameters. Because obviously the weight, this is a, 2 by 3 or whatever matrix, but in a real model, that would be a gigantic, gigantic matrix. So you get a lot of benefit by turning that R into something like, 8, 16, something of that size. Okay. And so then again, sort of there's tons and tons of flavors of this. So the core sort of idea behind LoRA is pretty similar between all of these, but there's lots of different ways specifically of implementing it in the exact matrices that you choose to apply it to, in sort of extra flavors that you can do on top of it. Dora, this is a very popular sort of edit to LoRA, where every weight matrix is decomposed into a magnitude and direction, and then the magnitude and direction are updated separately. And so that has shown to, I think, basically in every case work a little bit better than LoRA, but you don't add that much. Like when you decompose into magnitude and direction, you have a scalar and a matrix. And so you just have to update now one additional scalar, but because of the way that you've been able to separate those two components, you in general perform much better. So again, I'm not going to get necessarily too deep into all of these different flavors. We're going to choose a standard LoRA in the notebook that we go through, but just so that you're aware that there are lots of different ways of applying this that sort of have different benefits, some drawbacks in terms of the overall size. But yeah. Okay, I think that is the last slide that I have. So we can move on to talking about the notebook for today, but are there any questions about any of this before I move on to the notebook? Okay, and if questions pop up, feel free to ask them, even if it feels like the moment has passed. Okay, so in our GitHub, I have uploaded a notebook that's called PEFT LoRA Llama, which is basically we're gonna do PEFT in the flavor of LoRA on a llama. And so it's a very straightforward title. Um, you should be able to open in Collab. I have ran this notebook. So similar if you were with me on Friday, this notebook, even though it is PEFT, will take a little bit of time to run, not that long if you have access to a GPU. I used up all of my GPU compute on Colab without realizing that I had accidentally used it all up. So I didn't get to finish running this notebook. Um, but this is definitely one that you can run along with me, and you should be able to get to the point that you see some training because it is really quick to run, especially if you're able to get an A100, a little bit of A100 time, then that would be great. So if you change your runtime type and it does not tell you that you've used all your compute, then you should be able to run this as we work on it. But yes, it is very sad that I ran out of compute and I didn't notice it was happening either. um, okay. I think I saw, I lost my chat. I thought, oh, just to make sure, in your matrix multiplication, R is the vector of the few parameter that I change values of, right? Um, R is the Yeah, R is the rank of the matrix, which is a parameter that you choose that determines the size. So basically, larger R, you can choose R to be whatever you want. Typically, it's something very small, like 4, 8, 16, uh, 32, 64. It's but it's basically a free for you to choose parameter that just basically determines how many parameters are going to be added to the model and trainable. So because this is mostly just fixed to sort of make the math work out, it is because that dimension will drop out, you are sort of free to change it how you want. But if it's larger, more parameters are being added to the model. And so the model kind of has more flexibility to adapt, but also more parameters to learn. It'll cost more compute. If you make that smaller, much less of the model is going to adapt. So you might not have made it high enough to actually change the model significantly to adapt to your task, but you'll save much, much more compute by making that number smaller. To answer your question. Okay. So yes, feel free to, if you have access to some compute, try to run this along with me. You will need a Hugging Face token. You can swap out the model. I have done this with Llama 3.2 because it's kind of well, it was at the time that I made this notebook. It's not now the most recent Llama. I think Llama 4 came out. But this is a pretty up-to-date version of Llama 1 billion. So very, very small, but still a pretty powerful, super tiny LLM. And so it's a good one to train. I mean, for that reason that it's so small, but it's still really powerful. But Llama does require you to one, have a Hugging Face token, and two, to go to the Hugging Face page of Llama and ask for like permissions to use it. So um, if you go to the Hugging Face page for this particular model, there will be just a little like form that you have to fill out that gives, you put like your organization and you, I think, say like how you want to use the model. And then it will, I think, be a couple minutes before Meta gives you approval. I did tell recently somebody that I think it's impossible to get denied, and then they got denied actually from this model. I have no idea why. They had a Vanderbilt email. They said they were with Vanderbilt. So it is possible to be denied, apparently, but I think it's really rare. I think basically just say you're with Vanderbilt and you will be granted access to this model. But if for some reason you're denied, you can switch out this model ID for another Hugging Face model that does not have permissions and require you to fill out a form, um, and you should be okay. Okay. So those are the couple things that you'll need. And then I actually think similar to the reinforcement notebook that we did on Friday, we do use weights and biases in this. So that is another token that when you get to, it will ask you for. Um, okay. So as I said, I'm out of compute. I wasn't able to fully run this. I'm going to talk through it up until all the part where we set up the PEFT was able to run. So that is good. I'm going to talk through where I was able to get it to run through, but not rerun the cells myself because I do not have the compute right now, but feel free to run it on your own. So like I said, in this particular one, we are fine tuning Llama 3.2. And I wrote this notebook to be like a domain adaptation. So there's going to be a point in which we just can upload as many PDFs as we want, and it's just going to train on learning that data set. So a simple task of sort of being given additional information, trying to just learn what is inside of that data set. And so we're going to start with some really basic setup stuff. The one thing to really point out is that this package here, so from PEFT, we import LoRA config and get PEFT model. The PEFT library is that library that I was talking about, which has done a lot of the work for us and made it really, really simple to just add a little bit of PEFT weights to our model, and it'll handle it all during training. So you'll want to make sure that this imports right, although I think that all of these installs should be okay. And this is the package to sort of look into more. It's also made by Hugging Face. If you want to just read more about this particular library, this is the one that's doing a lot of our heavy lifting. So we're going to start by running the notebook. You can check if you have a GPU currently available by running this cell. And then here is where you will have to input that Hugging Face token in order to be given access in this notebook to Llama. And I think Umang put a link to get your token in the chat and also to that page where you have to request access. I think also this link will take you to the tokens page if you have one and you just need to be reminded about what it is. Okay. So, llama is the token, the key that we need to enter. When in this cell, when you enter it, a little password thing will pop up and you just enter exactly the token and hit enter, and that will like log you in and give you access to the model later. Okay. So in this cell, you should hopefully, if you have been granted access to Llama and your token is working properly, you should be able to load the model and the tokenizer directly from here. And so in this cell, we're just inspecting that we're able to load in the model and the tokenizer, how we think we should be able to load them in. Is the token only for this version of Llama? No, the token will be your general Hugging Face token, which means that anytime that you have like gone onto your Hugging Face account and gotten permission to use any model, like your Hugging Face token just attaches to you. So it's just Hugging Face's way of being like, oh, does this particular person have permission to this thing? So once you are logged into Hugging Face and you request access to Llama, your token will work to give you access to Llama. But if there's some other model um, somewhere on Hugging Face that needs separate permissions and you fill out a permission request to that, your same token, which now just identifies you, will also work to access that model. So your token is just a general identifier of you. However many models you've been given permission to, that token will give you access to if you enter it like this. And some Hugging Face models don't require any permission. So there are some that you could swap this out for, and then you would not even need to have your Hugging Face token entered because those models are just kind of free and open. Okay. So I don't want to spend too much time at the sort of beginning of this notebook. I had put in some extra things when I had made this notebook that um, I'm going to a little bit skip past where we sort of inspect how things are getting tokenized, just in the interest of making it to the PEFT parts. We don't have that much time before the hour. But yeah. So let's talk about loading in our data for fine tuning. So as I said, the goal of this particular notebook is to add additional domain specific information. So a general task of just creating a data set out of documents and then trying to insert that information into the model and have it just learn what is in the documents, learn directly off of the documents. So the way that we have the way that we're going to input that information is in the form of PDFs. And so we have to sort of organize the data such that, first of all, our PDFs can be read and cleaned. PDFs are kind of annoying documents at times. They have a lot of weird special characters in them or weird ways of being organized. So we're just going to have a few functions that we're going to have that clean up our PDFs a little bit. And then the other thing is that we are going to create these text chunks. The idea here is just to create from all of our documents, just like more bite-sized bits of information to learn. So instead of, if I upload a 20-page PDF versus a 5-page PDF, all of them are just going to get turned into little chunks of distinct sort of data points in this function. And so again, we're sort of going to, investigate how we look at a particular chunk and then see how it gets chunked up. Okay. So that's going to be our data set. We're going to input documents. It's going to just turn them into these neat little chunks, and that's going to be all of our data points that we're going to train on. So these are the functions that I was talking about, where we're going to extract our text from PDFs and then clean them. I think I made an assumption in this notebook that we're trying to learn some specific academic domain. So the assumption here is that it's academic papers are your PDFs. And so this clean academic text function was my attempt at removing some of the nuances of specifically academic texts that would not be helpful. It's not that one PDF is broken into 512 chunks, it's that every PDF is broken into chunks of size 512. So if your PDF was 20 pages, maybe that's 20 chunks. And if your PDF was 100 pages, that would be 100 chunks. So it's not a fixed number of chunks, it's a fixed size of chunk, which is 512. Okay. So then we are going to just format our text chunks in a way that Llama should understand a little bit better. So because we are using a model that is going to be able to respond to information already, we're going to just insert our information embedded into a prompt that is how it would respond. And so Llama has these tags for what the system says, what a user says, and then what it's supposed to respond back with. And so we're just going to format our data into the format that it wants things in so that we're not messing with the format it expects things in. So we're just going to tell it to learn information, insert that information, and then tell it to just respond that it's understood the information. So these things are not particularly going to do much. Like most of the information is going to be inside this clean text, but they are just going to preserve the way that it's sort of expecting to have pieces of information, which is with all these tags that it's kind of already understood the meaning of. So it already understands that assistant is it responding to things, that user is what you've said to it. And so we just want to kind of maintain that tag structure as we format our chunks for learning. Okay. So this is just going to be putting together all of that. So taking a document and chunking it is one step that we have to do. Cleaning that text, both removing all of the academic paper idiosyncrasies, is going to be another step that we have to do. And then just doing this last little formatting step is the final thing we're going to have to do to fully go from PDF into piece of text that can just feed directly into our model. And so we're just going to set up a full function that does all of those things. So loads, cleans, chunks, and gets it ready for training. Just we're going to sum that all up into this function. And so when we upload our documents, they're going to run through this function, which does all of those things we just talked about, and create a bunch of a data set based off of that. So when you run this cell, you should have just a button appear where you can choose files that you want to upload. When I originally made this notebook, I was training it to understand the concept of dialogic reading for a project that I was working on. So the PDFs that I had uploaded were all about dialogic reading, and I think that the notebook later talks about seeing if the model understands dialogic reading, or I think the questions that I ask it to probe its understanding are about dialogic reading, but you could choose whatever domain you want. If you have, a folder somewhere of papers about, I don't know, the effects of vitamin K2 in the body, you could put that whole body of knowledge into this and then test if it's learned some of the things you think it should know based on those papers. So whatever you want can go in here. And we'll see that it's going to read all those in, clean them, extract text, and create a total number of chunks. Now I will say, totally for testing, feel free to upload a very few number of chunks. Like if you just want to be sure, a very few documents to create a very small number of chunks. Just if you want to like run the code. But in general, this is probably too few. So I only uploaded, I think, like 3 PDFs, and so that didn't turn into a lot of data. I tried to give what I think very roughly would be the correct number of chunks if you actually wanted to see some good results and see it start to pick up some good domain knowledge. But if you just want to kind of get through the notebook, have it run, totally feel free to just upload like 2 PDFs. You're not going to have a lot of chunks, but it'll run blazing fast, which will be good to see. Okay, so now that we've done all the work to set up our data, let's talk about how we actually train this thing. And so one thing to note, so I did say at the top of this notebook that you could swap out llama for a different model that does not have Hugging Face permissions, but there are, with every model, a few sort of nuances. So llama in particular um, has particular like training precision of its internal numbers that might cause problems if you just swap out the model to one that doesn't have the same internal parameters. So I do recommend trying to run this notebook definitely for the first time, at least with llama 3.2, because a few things are set sort of assuming things are set up like for llama, although some other models might be able to just effortlessly kind of swap out. But it's one important thing to note that when we sort of set up the model, we have to keep in mind some sort of internal specifications that the model sort of expects and already had. Okay, so we are going to set up um, fine-tuning this thing. And there's going to be sort of regular fine-tuning parameters and then particular LoRa fine-tuning parameters. So we'll see how both of those things kind of fit together. I do make a note here about Llama also has a 3 billion version. So if you had the compute and wanted to, you also could totally, and that very easily you could swap out. You don't have to worry about the specifics and the precision of the numbers. Just swap out 1 billion for 3 billion, and that should also work. We're using 1 billion here because it's simply the smallest. Okay. So we are going to start by setting up our training arguments. And so training arguments are going to be just generally how the model is trained, and this is not necessary for PEFT, or it doesn't necessarily interact with PEFT. So PEFT, which is going to specifically be how we edit those weight matrices, is going to be a thing that's able to sit sort of on top of how you would set up additional training. And so all of this uh, sort of here is how you would still be setting up your training even without using PEFT. So just sort of setting some of those fundamental training arguments, saying where you want to save the model, how long are we training for, that type of stuff. Once we've already sort of loaded in and set up our model. But here in this one cell is where PEFT is going to be fully set up. And so you should be able to actually, in this particular code, toggle use PEFT as on and off if you just want to see what training without PEFT would look like. It'll take a long time. But just to sort of experiment with that, you can just shut this off and then none of this will load up. And actually the fine tuning will just proceed as full fine tuning. But instead, we are going to have use PEFT on, and that means that we are going to set up a PEFT configuration. We're calling the LoRa config because we want to do regular LoRa. Here is where we're going to set that R, so the rank of the matrix that we were talking about here. So this number, which again, if it's higher, means you're changing more of the model, but you're going to need more time. And if it's lower, you're changing less of the model, but it'll be even faster. So that's just a parameter that you're going to want to tweak to fit your particular use case. The alpha parameter is going to determine how those weight updates in LoRa are scaled. And so that, again, is a hyperparameter that you have some ability to sort of tweak and see how it works out. It's going to, yeah, just be one of these hyperparameters that takes a little bit of trial and error. LoRa dropout, we didn't talk too much about. There is a particular flavor of LoRa that's called dropout LoRa that I think has additional things that it does on top of it. But dropout is a technique in a regularizing technique in standard neural network applications that you can add to LoRa, and it's not the same thing exactly as dropout LoRa, but it just helps to sort of regularize and stabilize the way that learning happens. You don't need this parameter strictly. I think that this is just a very typical thing to have it set to. Target modules is going to be where you want to apply LoRa to. And so these we might be getting a little into the weeds. But here you can specify exactly the types of layers that you want to add LoRa to the weight matrices of. And so if you sort of know about standard transformer architectures, you have like Q, K, V matrices in the attention, so you can add LoRa to those or not. So here you can just specify all of the different places that you want to add LoRa to the specific matrices of. Yeah, and so you could specify, so as again, we sort of talked about here in the different LoRa flavors and also sort of in how generalized this application is, LoRA can be added to any and all and any combination of the weights of a model. And so you're sort of able to just like fully specify that um, in the target modules. Are rank and alpha to be thought of as parameters that are mostly determined by how different your data desired output is, or do things like model size or quantization also impact that choice? Um, I it yeah, I mean in practice it's both. So um yeah, if your task is super different, you might, yeah, like for instance, need a larger rank to adapt, but um it is sort of a balance where like if your model's also super small, maybe you can get away or you want a smaller rank for a smaller model to also change a smaller overall percentage of the model's weights. So it's a bit of both. And it really is also a bit of a trial and error thing. I think it's pretty common to just try to iteratively move up the rank until you sort of see the behavior that you want, for instance. So you could choose some standard value, and then if it's, not changing enough, you try to move the rank higher and see if that's better. But then if maybe you lose some information, like it adapted to your domain task really well, but now it no longer can describe what a zebra looks like, you roll that rank back because you've sort of changed too much of the model and lost some general knowledge. So it is very much a thing that you sort of balance and play with. It does depend on your task, but it does also depend on your model size, what sort of that right number is going to be. Okay, so once we have set up our PEFT configuration, we simply pass it to the model. So we just make a new version of our model that has PEFT already in it. We can print trainable parameters on this new model and get, like I was saying, that number that's going to tell us what percent of the total parameters of the model are now trainable, which is just a great way of knowing. It's a great summary way of knowing like how much am I about to change this model. So this can be super, super low if you want to say I barely am going to change the model, or a bit higher if you want to say, oh, I'm willing to change kind of a more significant chunk of this thing. Okay. So then, once we have set that up, the training proceeds basically exactly if you remember the reinforcement learning notebook, or if you've seen a training setup before, the way that you train this model is going to proceed basically exactly the same. So this model is now has baked into it our full PEFT config and all the things that we want to do there. And you just pass it to your trainer with the training arguments that you specified. And again, that PEF package in the back end, it's going to take care of all of the things that have to go into training with PEFT. And so that's great. It's again why we can just swap this out really easily, and you can simply turn this off, and all of the rest of the structure of this notebook is going to stay the same because these packages have made it super easy to add it in like that. And so then we just start the training loop with our classic um, training step where we're just going to, I think in here I just printed out a bunch of additional information, but we're just going to exactly how we normally do, set up the training, and then at the end, save the model. So once you have that trainer, it's super easy to start the training. And then you can watch, like I said, if you have compute, you can watch this training go down. It will be very fast, especially with the 1 billion parameter model, and especially if you put relatively few chunks of data. But even if you have sort of on the higher end, as long as you're on a GPU, it will be super quick. And then I am not able to fully show you because this was where I had to stop. This was where my training died. My access to compute died. And so I wasn't able to show these last few cells with real output. But when you run through it, you'll see that we can print out, for instance, like how many of the parameters are changed. We can print out the base model and just confirm that that did not change at all. So I think that here I ask if the models are identical just between the base parameters, just to confirm that that underlying model, all of the original weights, we didn't change at all. Those are identical. And the only thing that we trained was our new LoRA weights that we added. We can also do some comparisons between our original and our fine-tuned models. So similar to how in the reinforcement learning notebook, after training, we said, okay, what was this thing doing before? What is it doing now? We can do the same. So just set up a pipeline with the original model and set up a pipeline with our trained model. And we can just ask it a couple of questions and see if it has performed as we expect. So the last thing I will say, and then I will be done with this notebook, is that um, the one thing is that when you're reloading a model with PEFT, you're going to make sure that you use specifically a PEFT model. So again, in this cell, we have to just know if we did use PEFT or otherwise, how we're going to add in the weights because again, the PEF package will handle it for us. It has these built-in functions, but that are going to define adding back in those PEF matrices. Because remember, because they sort of exist as these like external matrices that can be like modularly added and removed, we need to specifically load our PEF weights and attach them to the model. So that's kind of the last thing to know about. But yeah. Is PEFT a transfer learning model? Um, I don't really think about it as transfer learning. I mean, I think I really think about it as just very low, like low level fine tuning. And so, I mean, I guess the way that it could be similar is because you could theoretically like pick and choose your PEFT weights, but I think I do really just think about it as like really like micro fine tuning, like really small fine tuning, rather than something that's more like a transfer learning. Okay. Um, well, yeah, I don't want to take up too much more time. I think we want to fit in a small break, and then Umang is going to tell us about RAG. But I will be around for office hours. So if you think of any questions, you run this notebook, any questions pop up, feel free to ask me then. Um, and Umang, I don't know how long. Do you want to take like a 10-minute break and then?
Sure, yeah. Let's do that.
Awesome. Okay. Well then, yeah, I guess everybody come back at 12:14. It just turned the minute according to my clock. And yeah, thanks.
All right, welcome back. Can everybody see my presentation? You can leave a thumbs up if you do. Perfect. Awesome. So my name is Umang. I'm senior data scientist at the DSI, and today I'm going to go over sort of an introduction to retrieval augmented generation, or RAG for short. This is a powerful technique that's become increasingly important in the AI landscape, especially when working with LLMs and some sort of private data or data that you just don't want out there. So here's what we'll cover today. We'll start with a quick introduction to RAG, talk about what it is, why it matters, and when you might want to use it. We'll do a deep dive into the architecture and explore some key components of the RAG pipeline and introduce some pseudocode. And then at the very end, we'll go over some quick setup for Google Colab and LangChain to prepare ourselves for Wednesday's sort of hands-on coding session where we'll actually get to take what we learned today and actually implement it on your own data. So, what is RAG? At its core, RAG kind of combines two processes. First, which is the retrieval of relevant knowledge, which is followed by generation by an LLM. The key insight here is that the context or the data is injected at query time. We don't modify any of the model's weights, which basically means RAG works with practically any LLM out there, whether it's from OpenAI, Anthropic, Google, or just some, open source model. So the fundamental idea here is that, you can that makes RAG so powerful is that you can keep your private or fast changing data completely outside of the model and still get personalized and context aware answers. It's like giving LLMs access to your specific documents or knowledge base without having to do all the training that we just saw. And I'll talk a little bit about, when you actually still might want to train, but let's first look at why would you choose RAG? And let me just pull up my um, chat as well. Okay, does that mean the knowledge goes in the attention block instead of the multi-layered perceptron? It kind of does. It'll become a little bit more clear as we go into the details of what RAG is, but that's a good question. Um, So let's first quickly talk about why you might even want to use RAG. So the first compelling reason, of course, is, low upfront cost. You're not doing those expensive training runs. You don't need high performance computing infrastructure. You can just get started on a simple laptop. Second is whenever your documents change and you're dealing with continuously changing data, you can simply re-embed that data, a process that takes seconds compared to taking hours or even days when you're training. The third is there's like a much smaller operational risk. So if you do make changes to your pipeline of RAG and you don't like the results, it's very easy to just go back to what was working because the model weights stay frozen, the model itself is not changing. So like any of those things that happen when you do some sort of training, like catastrophic forgetting, just cannot happen. And then finally, of course, there's excellent data governance and IP safety, both if both your embedding models and LLMs are run locally and you're storing your data on a private vector store, it's never exposed to an external service. It's like basically running everything on your computer, so your safety is as safe as your own personal computer. But there might be cases where fine-tuning is the better option. So imagine if you're working with really highly specific domain language. For example, medical notes at Vanderbilt University with acronyms that just don't exist in regular speech, but also change from hospital to hospital. This specialized level of vocabulary might just be too nuanced for a generic embedding and prompt to catch consistently. So in a situation like that, you might find that RAG just doesn't work. It'll work a little bit, but it won't work consistently. And so you'll need to likely do some fine tuning there. Another place where you might see that RAG might not work is when you're working with really specific output styles, such as legal wording, poetry, code patterns. And again, your prompt can't just reliably enforce that every single time. Another thing to think about is latency budgets. So in a sort of application where every millisecond counts, The vector search and retrieval steps in RAG might be the sort of block in getting things to work quickly. It does take a second to do all of that retrieval. So, if you were working with millions of queries, this might become problematic. And of course, finally, if you face context length limits and certain terms appear in nearly every prompt, embedding that over and over again just becomes wasteful and expensive. And so you might just find that baking some of that information into the model weights through fine tuning just makes more sense. Any quick questions about that? Okay, so let's look at some quick use cases. So enterprise search assistants where you want to, ask internal policies or research documents. RAG is perfect here because these documents tend to change frequently. Customer support chatbots that might need access to product manuals, FAQs, ticket history. And so RAG can be very useful here as well. Academic literature co-pilots, retrieving papers, using something like O3 to do the sort of literature review for you, but then embedding those documents and using sort of similarity search to basically create a database that you can use for quick Q&A against this large corpus of academic documents. And of course, code-based Q&A where you might want to, connect it to a repository and then explain functions works really well in these kind of scenarios. So let's take a look at what RAG actually looks like. This is a high-level pipeline. So we start with data ingestion, and we basically read in the documents, you split up the text into manageable chunks, and then you create embeddings out of those, which are vector representations that capture their semantic meaning. These vectors are then stored in a vector database for quick retrieval. And then when a user comes in, we retrieve the most relevant chunks from that vector store using some sort of similarity search. We then augment the original prompt by merging it with the relevant context. And then finally, we get an LLM to generate an answer based on the context and the prompt and all the information that you give it, which just gives the LLM access to this more specified information. So let's talk about document ingestion and loaders. Um, the goal here is basically to take raw data in whatever format it may be, like CSVs, PDFs, Slack threads, Google Drive, folders, files, and so on, into a document object that LangChain can work with. And LangChain provides numerous integrations for different data sources, but the basic pattern across all of these data sources is simply loader.load. This function right here. It returns a list of documents based on whatever loader you're using. So this could have been a PDF loader, so you just say PDF loader.load, or Google Drive loader, Google Drive loader.load. You would need to obviously do a little bit of setup depending on what kind of loader you're using, but it's pretty much as simple as that. And then once loaded, the documents sort of flow into the text splitting stage. And this is some pseudocode, although it might actually work, apart from, of course, you missing the file path. It's as simple as this. You load a PyPDF loader from LangChain community documents. You set a sort of empty list full of pages, and then this is simple as, for the page in whatever document the loader is loading, you just basically load each page one at a time. The same pattern is consistent across most document loaders. So switching between document types is super simple. You just change out this little bit. So the next step that comes is splitting these documents. And there's several important reasons why you might want to split. Sorry, give me a second. My screen went out for some reason. Okay, I just lost my monitor. Oh, there it is. It's back. Okay, sorry about that. Okay, so why do we want to split documents? One, of course, is you want to be able to handle documents of different length easily. Splitting helps us handle documents of these varying lengths uniformly. It also ensures that we stay within the LLM or the tokenizer input limits because most models have a context length that isn't too big, especially if you're working locally, you're probably working with a model which has a smaller context length. But perhaps most importantly, splitting chunks produces higher quality and focused embeddings. Imagine you had a document that talks about multiple topics. Creating an embedding of that single document with so many different topics is going to create sort of this muddy, non-specific embedding. But if you had split that document up into smaller focused chunks, you're going to have embeddings that have a clear semantic signal. So LangChain provides four main families of text splitters. One is simply the easiest, which is length-based splitters. The next is text structured or recursive splitters. There are document structured splitters, and then the most advanced are semantic splitters. So looking at them in detail, length-based basically means, you choose a fixed token or character window. They're fast, they're predictable, and your documents are just split up into these equal-sized windows. There's a question. If you split documents, won't you end up with a lot more embeddings? Yes, you will, but these embeddings are very, very lightweight. They don't take up too much memory, even on your computer. They're very, very lightweight, so that is usually not a concern. But yes, you will end up with way more embeddings. Um, the next type is recursive, which basically walks the hierarchy of the text structure. So this could be paragraphs or sentences or words. It depends on how you set it up. But the idea is to just preserve the natural flow of the document. Document structured splitters use sort of the actual formatting of the document. So if you had a markdown document, you could split on markdown headers, HTML tags, JSON keys, code blocks. So those can be pretty useful when working with different types of documents. And finally, semantic splitters basically do the splitting, but they use a sliding window of embeddings. And I'll go into the details of what this looks like on Wednesday. But basically, they look at they start embedding the documents in certain chunks, and they decide to split them when the embeddings are different enough. So it's like constantly taking this sliding window of embeddings, and when it sees that the embeddings have sufficiently changed from what it was just looking at, it splits them, and those are now two different documents. This can be obviously a little bit problematic because you're also likely using an LLM or a really good embedding model, so there's just a higher computational cost. And again, LangChain makes it really easy to actually implement this. So for example, this is the recursive character text splitter. And all you need to do is give it a chunk size, say if there's any overlap between the chunks. Overlap helps because now the chunks have physically something that's tying them together, which can be helpful or can be problematic. It really depends on your type of data. So you really need to think about how you want to split this up. And then it's just, once you've defined the splitter, it's just splitter.split text. And that tends to remain the same no matter what kind of splitter you're using. The next thing is the actual embedding model. So the idea here is basically an embedding model maps the text that you have to a fixed length vector, essentially sort of creating this semantic fingerprint of the content. These embeddings are what enable the semantic search, clustering, recommendation systems, whatever you want to make based on meaning rather than just keywords, which is what NLP has mostly been like usually so far. In the RAG process, we have two key steps involving embeddings. First, we just embed both the user's query and the document chunks, and then we compare these user query vectors to the document chunk vectors and figure out which are the most relevant chunks to use. And again, they make this very, very straightforward. You just grab embeddings. Here's an example of grabbing OpenAI's standard embeddings, where you just say from LangChain OpenAI, import OpenAI embeddings. You establish the embedding model. It defaults to, I think, text embedding 3 large at the moment. And then you just do embeddings model dot embed documents. You can pass in documents. Here, each one of these, because they're separated by commas in a list, are separate documents. And so you essentially end up with 5 documents, each with embeddings of this dimension, 1536, because this is the dimensions that the embedding model from OpenAI throws out. So, measuring similarity. This is where things get a little bit interesting. Once we have the embeddings, we need to compare them to find sort of the similar content, and there are several ways to measure similarity. Although cosine similarity is, which is basically what measures the angle between vectors, is the most common metric for texts. Dot product is used sometimes for some of the more dense embedding models, although I've never used that. And Euclidean distance is just generally less common for NLP tasks. It is very important that you use the similarity metric that is recommended by your embedding provider. For example, OpenAI recommends that you use cosine similarity, but there might be, a different embedding model that recommends a sort of different embedding, a different similarity metric. But here's an example of how you might just, implement a cosine similarity. Here we're doing it very manually, but in practice, built into LangChain just very easily grab or like get similar documents. It's doing this under the hood where it's just actually calculating the cosine similarity, but LangChain makes this very easy for us. Okay, moving forward. It's important to kind of think about which embedding model you're using. Uh, the first thing to think about is domain fit. There are general purpose models as well as specialized ones for code or biomedical text or legal documents and so on. So it's important to think about, what kind of data you're working with. If it's just very generalized, you can probably just get away with like an OpenAI embedding. But if you are specifically trying to build sort of a RAG bot that looks at specific biomedical or hospital notes text, you might want to consider using a different embedding model. Vector size versus latency, because larger isn't always better. Sometimes a smaller, faster embedding model will work just as well. It takes a little bit of, experimenting, but you'll usually find that bigger isn't always better here because it just costs more to run a larger embedding model. And then, of course, as I said, cost. So something to think about is when you're using OpenAI embeddings, which is sort of the go-to, you are paying for that, but you could also just get a local embedding model from Hugging Face and run that locally. That just depends on how big that model is and if you can run it on your computer. All right, any questions so far? Cool. Oh, there's a question here. When you're dealing with data where chronology, narrative order matters, can that be easily captured into the vector database just from order in the document, or does it take more careful, specialized ingest? Yes, so this is definitely something you need to think about, especially when working with documents where structure also matters. For example, CSV files. So as you know, a CSV file is just a comma separated, large document where the first row is going to be the column headers and everything else is just going to be numbers. So imagine if we just had a CSV splitter, or we just used a splitter that isn't paying attention to the structure of the document. Your first chunk is going to have those column headers, but every subsequent chunk is just going to be numbers, which don't really mean anything. So this is where choosing a specific type of splitter becomes important. CSV splitters actually split row by row and also include the actual column headers every single time, which makes it a little bit more useful. Um, but yeah, so if order matters in your text data, that little bit of overlap that we saw back here, chunk overlap, here it's set to 0, but you could set this to something bigger. This does kind of introduce some continuity between your chunks. So when a sort of semantic search is happening, it will at least pull those similar chunks together. And then based on how many chunks you're pulling and how you've set it up, uh, you'll pull that consistency across chunks as well. Let's see. How does an embedding model actually work? Perfect. Um, that's exactly where I was going. So let's compare legacy embedding approaches like Word2Vec with modern embeddings in the context of RAG. So Word2Vec used to basically generate one vector per word or token. They have limited context awareness. Only nearby words influence the meaning. These systems require aggregating many word vectors together to compare passages, which just isn't ideal because they perform poorly on sort of full document relevance tasks. Modern sentence or chunk embeddings, which is what embedding models look like today, create one vector per chunk of text. They use transformer attention mechanisms within the embedding model to understand the broader context and encode the semantics of entire paragraphs and not just individual words. So this makes them a lot better for RAG, which kind of enables clean document level retrieval. And chunk size is of course tunable, so that's the most important thing, uh, along with of course your context length. If you know what your chunks actually look like, it makes it a lot more usable. Just blindly chunking it up into, 1,000 character chunks will likely almost always give you some issues. There's another question. During RAG, does the model learn from the prompt injected queries it gets, or is it just like it fully doesn't know or hasn't learned information regarding the documents stored in? So the model isn't learning anything. It's doing what we call in-context learning. So the weights are not changing. It's just kind of internally reasoning against all the information that you've provided it with. It's kind of why good prompts work better than bad prompts. It's just you're providing it with better content, better instructions that gives it the ability to answer your questions better. The model itself is not changing whatsoever. What are the downsides of modern embeddings? It's more compute heavy. That's kind of about it. And of course, if you want to use OpenAI embeddings, which in my opinion, in my experience, have been the best embeddings, you do end up exposing your data to that API. So that's just something that's kind of annoying, but there are now uh, newer open source embedding models being made available on Hugging Face that are definitely rivaling OpenAI's embedding models in terms of quality. Awesome. Let me know if there are more questions. I'll keep monitoring the chat. So, similarity search. So this is kind of what the workflow looks like. A user comes in with a query, something like, what causes tides? And this query gets embedded into its own vector. We compare this vector to stored chunk vectors. So these have been pre-computed. So we're not doing that computation at the time of query. It's just existing in sort of this local store. And then finally, we rank the results, return the top K most similar chunks. Top K is determined by what you set it to. So if you want your model to be provided with 10 chunks of information, K will be 10. If you wanted just to have one chunk, that's K will be 1. The vectors are compared using some sort of cosine similarity or another metric. And then those that are most semantically similar to the query are injected into the LLM prompt along with the query. So one really interesting question that came up in office hours on Friday was how do embeddings actually know what's similar? So, each chunk becomes a vector, which is like assigning it a point in a high dimensional space based on its meaning. And similar meanings result in closer points. So during model training, the training of the embedding model, examples with related meanings are pulled closer together in that space. At runtime, this model doesn't explicitly like compare these chunks. It just gives each one a coordinate. And then all we're doing is math, like cosine similarity to find the closest points. So chunk size does matter a lot in this process. If the chunks are too small, they just don't contain enough meaning to position well, which will result in lower quality vectors. And if the chunks are too large, they'll include a lot of irrelevant information that makes the computation more noisy. So you're just maybe giving the LLM too much information and therefore opening up its ability to hallucinate a little bit. Yes, the slides will be available. I will make these available right after the session. Cool. So the next thing that comes are vector stores, which are these specialized data stores that index embeddings. These enable fast similarity-based search over unstructured data like text, images, or audio. We'll focus on text, but you can totally do this with other modalities as well. In a typical RAG flow, we store the embeddings in chunks in a vector database. Then we embed the user's query when it arrives. Then we retrieve the top k most similar chunks from this vector store to provide the context for the LLM. Does the entire document have an embedding? The entire chunk has an embedding. The document could have an embedding in its entirety if you decided to just keep the entire document as a single chunk, but it's the chunks that are individually embedded. Um, Moving forward. So again, LangChain makes it really easy for us to work with these vector stores. And regardless of what implementation of vector store you're using, because there are lots of third-party vector stores that you can use, you can also kind of use one that's in memory, which is sort of my go-to. They all kind of work the same. There's an add documents function for storing new documents. There's a delete for removing documents by an ID. And then there's just the similarity search. So you don't actually have to write the cosine similarity. It's just like vector store dot similarity search. And that helps you find the documents to query. And you can kind of play around with what similarity search metric it's using by default by just passing in a sort of parameter in here. Let's see. And yeah, so this is again kind of what it would look like. You import a couple of things from LangChain, you give it the embedding model, you create a vector store. So this is the most simple vector store where it's in-memory vector store. You're just passing in the embedding model. Your documents are in sort of a list where this is one document, which is chocolate chip pancakes, and you gave it some metadata called tweet. And another document that is for class cloudy, and then you said this specific document has metadata news. And then all you do is vector store.add documents, and then you add them. Very simple. What is the difference between different vector databases and how would you pick between them? So most vector databases are mostly the same. The biggest thing to consider is it a local vector store or is it a vector store that's hosted somewhere? So that decision obviously comes from what kind of data you're using. The other thing to consider is some vector stores work really well with extremely large corpuses because they have built-in indexing algorithms that work better than just the kind of base indexing algorithms that most of these use. So you might find if, your retrieval step is just taking way too long with a certain vector store, you might find a different vector store that just works better with larger amounts of information. But I kind of tend to just stick to the same one that's local, one that's um, hosted. I think I usually default to Deep Lake for hosted ones and just sort of the in-memory or face vector store for local stuff. But that's kind of really up to you. All right, moving forward. So yeah, as I mentioned earlier, metric choices could be cosine, Euclidean dot product. Pick the one recommended by your embedding provider. Most of these will default to cosine similarity, but you can always change that if you find that isn't working for you. And again, this will just return a list of documents, a list of document objects ranked by similarity. So the most similar document will be first, followed by how many ever. So here you will get 4 documents ranked by similarity. Another powerful thing about vector stores is that they can combine this sort of semantic search, which they are doing by cosine similarity, with structured filters. So as I showed here, we're passing in these sort of metadatas. And so it makes it very powerful if you can search not only according to what the content of the data is, but also kind of point it into a specific sort of subset of documents. So that works really well because you can just say, similarity search. The actual query is LangChain abstractions. You're just grabbing 2 documents and then you're saying filter only tweets. So I only want in my entire corpus, I only want to look at the documents that are tweets. This makes it very, very powerful because you might have, a very kind of um, varied set of documents. So this just allows you to have a little bit more control over what it is that is getting picked. Beyond basic search, there are also, in addition to just doing cosine similarity and the sort of filtering based on metadata, you can do a hybrid search, which is keyword plus vector similarity. You can do MMR ranking, which is maximal marginal relevance, which just diversifies the results and avoids you to having near duplicate chunks. And then scalability also, most cloud stores like Pinecone, Deep Lake, they expose the same API, which is just makes it very easy. You just swap them out if one sort of vector store just isn't working for you. And then LangChain has tons of these available on their website and has really, really good documentation to support these integrations. Do models that search the web use RAG? Sometimes, but not always. It really depends on how that web agent is set up. So that web agent could just, go to a website and pull text and just put that text into context. And so then it's just kind of not doing RAG. But what it could also do is pull the entire website, split it up into chunks, do a similarity search, and then give the model more sort of narrowed, focused data. It just totally depends on how that LLM provider has set up that agent. As far as I know, OpenAI's sort of search just throws things into context because they're also working with models that have, 128,000 token context length. So they're less concerned. But I could also be totally wrong because they don't tell us how they set these up. But yeah, it's is all context weighed equally? Yes, when you're throwing things into even with RAG, when you're just throwing things into context, all you're basically doing is you have your prompt, you have your context in chunks provided as document objects, and then you have your query at the very end. It's just like one very long prompt that's going to the LLM. So they are all weighed equally. Yep. But, these are, as I said, ranked by similarity. So that just inherently kind of adds some sort of importance to the chunks that are provided first, technically. But there's no like actual mechanism that's weighing a chunk more than the others. All right. Where was I? Okay. Um, the next thing that comes is the actual retrievers. So we've looked at how to do the semantic search. We've looked at vector stores that have built-in sort of a retriever, which is just a similarity search. But retrievers themselves provide a uniform interface over many, many backends, which includes vector databases, search APIs, SQL or graph databases, and lexical search engines. The input to a retriever is always just a natural language query string, which is what the user provides, and the output will be the list of documents. But there's a lot of nuance that goes into figuring out how you want to set up your retriever system. So for most retrievers, it's implementing this get relevant documents based on a query string, which is exposed by this invoke function in LangChain. So it's literally just you take your vector store, you convert it into a retriever, and then you just do retriever.invoke what causes tides. And then it does all of the stuff under the hood for you. Let's see. Yeah, so this is an example where you have a vector store, what you've created. This could be any vector store you want. You just do vector store dot as a retriever. It converts it into a retriever. And then you just do retriever dot invoke, give it a query, and that's just kind of how it works. It does everything under the hood for you. You don't really need to think about it. But there are very advanced retrieval techniques that we'll talk about mostly on Wednesday, that really allow you to have a lot more control over exactly how things are being retrieved, where they're being retrieved from, when they're being retrieved based on the context of the question. You can have all sorts of control over that. Some of those techniques start becoming a little agentic, which Dr. Bell will go over next week. But the retrievers can be very, very powerful. All right, let's take a look. All right, the next thing that comes up in RAG is the actual prompt engineering and the augmentation of data that you're doing. So the goal of augmentation is to inject the right external context into the LLM prompt, which basically involves, concatenating, which is putting at the end retrieve chunks into a context variable, keeping the total tokens under the model's limit, and giving the model clear rules about tone, length, citations, and sort of fallback behavior when it doesn't find the right information. So here's an example of a robust RAG prompt template where it says you're an assistant for a question answering task. It's good to tell it what the role of the actual system that you're building is. We found it important to actually tell it that use only the context below, because otherwise, if you're using a large model like GPT-4o, it does have a very vast knowledge of the world on its own. But if you want to limit the number of hallucinations and sort of information that it gets from just its own knowledge, it's helpful to say use only the context below. And then um, you just say answer concisely if you wanted to do that. If unsure, say I don't know. That's really, really important. And then have it cite sources. So then it'll just kind of use the metadata of the actual context that you're providing to just say, okay, this came from this document. Why does prompt quality matter? So here's an example of a weak prompt and an improved prompt. So the first prompt is just answer the question. You give it the question, you give it the documents. So there's no guidance on using the context. So it will, augment this context with information that it knows on its own. And there's no instructions for what it should do when there's uncertainty. And therefore, this just increases the risk of hallucination. But if we give it clear usage rules, it limits the hallucinations. The concise length also helps keep things within the sort of model's token limits. And you have this sort of built-in fallback response where you can say, if the answer isn't found, say so. So this really helps kind of guide the model into giving you better responses and keeping it grounded. So this is kind of a full RAG pipeline, end to end. Very, very straightforward. This is mostly pseudocode, but some of this will actually work, and we'll see on Wednesday that it is pretty similar to how you would actually get this to run. So the first thing you'd need to import, a chat OpenAI, and then a system message and a human message. The system message is usually sort of the prompt. The human message is the query coming in from the user. So you first set up sort of system prompt, like you're an assistant for question answering. Use the context to answer the question. If you don't know the answer, you say you don't know, and then you can ask it to be concise. And then you pass in context as this sort of object here. And then there's a user question. You can just pass that in as a string. Let's see. So you create a retriever from your documents. You've already done that. This is done before you actually ask the question. You split them up. You format the system prompt with context. So basically, you're taking this context object here and filling that up with whatever document text that you grab from the retriever. And then finally, you set up a model. Chat OpenAI as a built-in function from LangChain that just references the OpenAI API. You give it a model, you give it a temperature if you want to kind of play around with that. And then it's as simple as model.invoke system message, which is this formatted prompt that you had, human message, which is the actual content of the question, and then that's about it. And it's really that simple. We'll see on Friday how we can make this more, on Wednesday, how we can make this more comprehensive. But at its base, it really is about 10 lines of code to set up a full RAG chatbot. A few common pitfalls that I have. Yes, I'll get to the temperature in just a second. A few common pitfalls that I've seen, of course, that I've mentioned is chunking that's too small or too large. This just results in poor context, and your RAG bot just will hallucinate a lot and come up with things that aren't actually in your documents. Embedding model selection can also have a huge impact. I almost always try and use OpenAI embeddings. I've found them to work the best. But if you are working with private data, there is, I believe, a new embedding model called Modern BERT, I believe, that works pretty well as well for sort of private data. And then finally, of course, hallucinations happen a lot, but there are a lot of ways that you can get around it and enforce it to not hallucinate. And we will go over some of those techniques next time. There's a question about temperature. So temperature here is just a parameter on most LLMs, which kind of allow the model a little bit more or less flexibility when it comes to actually selecting the next token. So as Jesse mentioned last week, these models are essentially, predicting the next token. And when they do that, they create a probability distribution across all possible tokens. So a higher temperature would basically give the model more flexibility, and it would allow it to choose tokens that are usually less common. And a lower temperature will, like a temperature of 0, will almost make it close to deterministic, where it will just pick the most likely token every single time. So this tends to make the model responses more concise, but also just more less creative. So usually if you were working with something that, you wanted ChatGPT to be creative in its writing style and just be, not so formulaic in its response, a higher temperature will just make it more creative. And this tends to work with most models, have sort of a temperature parameter that you can play around with. But in a RAG setting, I've found lower temperatures are better. You don't really want it to have that flexibility. You really just want it to stick to what is being given to it. So a lower temperature is better for a RAG type situation. Ooh, other questions? All right. So in context learning. So this is sort of a ability of LLMs that kind of just came up as these models became bigger. Something that we didn't really expect them to do so well at least initially. And it's just their ability to take whatever information that you give them in context, in the prompt, and sort of reason against it, not in sort of a reasoning model sense, but reason against it as GPT-4o, a GPT-4o type model would. And it seems to be a very, very powerful technique to improve the sort of knowledge that these models have built in, or at least augment them. One really, really fascinating example of in-context learning was when Claude 3 first came out, and they had this really, really massive, I think, million or 10 million token context length. And what they gave to this model was a book in a language that the model had never seen. And basically they put the entire book, which was sort of a reference manual on how to learn and speak that language, into context for this model, and then started asking it questions in that language. And it did really, really well to actually respond in that language, which it had never seen in its training data before. And it basically spoke at the level at which you would expect a human to speak at after they kind of studied that book for a while. So in context learning is really, really powerful and is part of what makes RAG really powerful. Um, Abby, do you want to elaborate on that a little bit?
Um, I don't know if I have anything
Yeah,
to
like I
really
will say
say.
it's
I think,
not just reasoning because it's not doing reasoning in the way reasoning models do. It's just using the context that it's been given and using that to predict the next token, and that just changes the probability distributions of whatever it's predicting next to a great extent that it becomes knowledgeable about whatever context that's been given to it and is able to use that to draw inferences from it.
yeah, I think that they are similar in ways to each other. Um, but I think it's like I maybe the way to think about it is like input versus output tokens. So like when you add stuff to in context, it's all like at front, up front, and then tokens generated later have that to go off of. but like chain of thought, which I think is more similar to reasoning, is like it's not in the prompt originally, but then by the model being forced to produce this, what it produces after it produces this bit of chain of thought or reasoning edits what comes after to also include all that information. So like it's mostly like where that takes place, I think that is
Yeah,
different.
cool. Can you apply fine-tuning to the RAG process, for example, the way it ranks the information it retrieves? Absolutely, yeah. So the retrieval part of RAG is really where the most advances are happening at the moment. And of course, there's also this sub part of query enhancement. But there are definitely tons of ways where you can change the way it's grabbing the information, change the way it's ranking the information. Um, and most of these are built into LangChain. And we'll go over some of these techniques on Wednesday. Um, but generally, the two main ways that I've seen people enhance RAG is using more complex retrieval methods, which usually tends to require some bit of custom Python programming, or actually query enhancement, where you take the user's query, you pass that into an LLM first without any other additional context, and you ask it to create a document or like a hypothetical document based off of the user's query. And then what you do is use that hypothetical document as input and use that to compare it to the chunks that you've already embedded, which is which basically allows, imagine your user gave you a query that is very generic and not focused. By creating this hypothetical document using the user's actual query, you're able to do the semantic comparisons better because now you're comparing a much larger document that has more context and more relevance to the actual embedded content that you have. So you can do that similarity search better. You pull in better chunks, and then you compare those chunks to the user's original query, and that tends to give a better um, response. And I think that process is called hide, which is hypothetical document embedding. I'll mention a little bit of that on Wednesday, but I do believe LangChain also has built in a way to do that fairly easily. Cool. So for Wednesday, it will be great if everybody can be prepared with just a Google Colab account, just where we don't need GPUs, we just need to be able to run some simple code on a CPU. So no no compute heavy stuff on Wednesday. We will be using LangChain version 0.3 or above. So it'd be good if you want to kind of like get a primer for that. We'll go over the basics of LangChain, but LangChain is a very, very extensive library. So I would definitely take a look at it if you have some time. We'll be programming in Python. And then if you can, try and get an OpenAI API key. This does require a credit card, but LangChain does make it very straightforward to use an OpenAI model. But if that's an issue, you can also just create a free Google AI API key, and we'll have some code chunks that will allow you to just swap out the OpenAI examples with Google API. But I believe that's it. Yeah, and also for Wednesday, if you have, a small corpus of documents, PDFs, text documents, docx, CVS, CSV, JSON, whatever you care about, whatever you have, just be ready with some of those. Ensure that they're non-private because we won't be using local models just yet. And then just have it available locally or on Google Drive, and then think about a few queries that you'd love a bot to answer using those documents. My hope is that at the end of Wednesday, after we've learned how to create our own RAG bots, you'll have some time to kind of implement this against your own data and see how you can use RAG with your own documents. We'll be here for office hours. I believe I'm 3 minutes over. Sorry about that. But We'll be here for office hours from now for the next hour, so happy to answer any other questions. Thank you. Thank you.
Hey, Umang, question, sort of follow on from Friday.
Mhm.
I was thinking of the cosine similarity basically assumes, or it doesn't really take into account the length of the vector at all. It doesn't. I mean, just mathematically, it doesn't take into account the length of the vector, just the angles, right?
Mhm.
So basically just putting everything on a unit circle and fitting it in there, and when we're doing cosine similarity, as opposed to like there's obviously information in the length of the vector, but it doesn't sound like most similarities consider that. Like they don't do a simple dot product, which would take into account the length.
Right.
And why is the convention moved to cosine similarity, which seems to give up some of this information?
Um, Why cosine similarity? I'm not sure. However, yes, you're right about, embedding or document length and chunk length having valuable information. And so there are techniques like hierarchically structuring your actual vectorized data that allows you to go from this like high level representation of your documents to a lower, deeper level representation of documents and doing sort of a filterized search that allows you to kind of still get at the details by using higher level documents. And it might be a little bit, it's kind of how I was saying, you can use summary documents and then use those summary documents to guide you to a more detailed chunk.
Mm-hmm.
That's kind of one way to get around that length issue because also, creating this very large chunk, very, very large length chunk will also be bad because then your just embeddings are possibly just too muddy, generalized, and not focused. So there's always value in making your chunks smaller, but intelligently smaller. Um, but there are ways to kind of ensure that, even with those larger documents which have a lot of text, you're able to get at them with a way that's not just throwing the entire document in there. Because yeah, things get lost when there's um, length issues. Do either of you know why cosine similarity? I've never really thought about that.
I think one, there's like a really tiny thing where it's just like a little bit computationally like less demanding, just like a little bit, because you
Oh,
can
it
have the
oh it is, yeah, for sure, yeah.
But then I think also like when you add in the magnitude of the vectors, very strongly like represented ideas or concepts in the LLM tend to have higher like magnitudes. And so like you can have like something that's like kind of less sort of interesting, right? And it's being pulled like it has more similarity to this thing with the higher magnitude because the values because it's more represented, right? And so
Mm-hmm.
like kind of the cosine similarity helps you to kind of get around that. But it also like Umang was saying, like do the thing that's suggested by the provider. So if it's saying that cosine similarity is the way to go, like that's the one that you should like go with for that provider. But if they're like, hey, we are really, excited about Euclidean distance and that's the one that we use and that's producing the best results for us, then that would be likely the way to at least minimally start with and see how to change it after that if you're not getting the results that you want.
Mm-hmm. It seems like in like the word to vec example, like the king, queen, man, woman, that's not using, I think, that's not using cosine similarity, is it? It's using like it's like looking at the relational difference between the vectors, right? So like king and queen have a similar distance than man and woman. So man and woman, the difference between those two vectors are going to be similar to the difference between king and queen. So there, I don't see the use. It seems like for like word embeddings, like BERT embeddings or whatever, it's more you're looking at, say, Euclidean distance or yeah, vector difference. Whereas for RAG, where you're doing like similarity searches, you're using maybe cosine similarity. Is that true, or is that um that's how I think of word to vec a little bit.
I don't even know so I don't really think of, so I think about them as doing like similar things. It's just the question of the representation. I'm trying to think about like the examples that I've seen about how people are doing like the vector math, usually when they're trying to demonstrate things about word to vec. I feel like I usually see it represented as it's like full vector behavior, like vector math.
Yeah.
So I think I think it's depending on how the provider is implementing things. Like it's just interesting, like at high dimensions that people are using Euclidean distance because like it has, I mean, sometimes maybe that's not the best one to use. So I mean, I think it just depends on how someone is training their model and what they kind of expect it to behave as and how they want to use those embeddings.
When you guys use BERT embeddings or embeddings from like an LLM, like how do you guys use them? Like what are some of the higher use cases? Most separate from RAG, let's just say. I mean, I don't see it as a RAG application, or maybe is it used as inputs to RAG, or
Wait, what's the question?
like, I've been told like you can get BERT embeddings or
Mhm.
like, and so when are those usually used? Like in what applications or yeah, are they not used for RAG, are they? RAG is probably something like where a set of documents are basically they create their own vectors, I'm guessing, and they put them in store them someplace.
So when you have like an encoder model, a lot of times people are using those things for like similarity matching, right? And that really you would see it a lot with RAG. So although
Mm.
they may not be using it specifically for RAG, the lot of the use case of embedding models does tend to be RAG because
Mm.
what you're always trying to do is you're trying to like use this query or some part of the query and find the relevant documents for it. And so like the whole thing is like we need to create these embeddings so that we can create an embedding from this other thing and then match and see which are the closest ones. So we return those back into context. So are you saying like very specifically BERT? Like what is the use case of BERT only this? Or is it just like what are the use cases of like embedding models outside of RAG?
Like embedding models where you like take the penultimate layer of them, I think is called the embeddings. Like I guess BERT, like I've used a long time ago some applications of BERT embeddings where you're not actually looking for the outputs, but you grab the embeddings of the words so you can do further processing. Um, and I don't know, I've used it a couple of years ago, and I was just curious on um how does that differ than say using embeddings in a vector database?
Hold on,
How do the embeddings from BERT differ from the embeddings from like vector database?
hold on. So let us retire very quickly the word embeddings. We're just going to retire that real quick and we're going to call it hidden states because
Okay.
this is the thing that is the output of like your embedding model or kind of like any body of a transformer. So we're going to call it hidden states. So does that
Okay.
change any of your question just then? Because there are other kinds of embeddings in these models, but are you talking about the output of this model, like the hidden state?
Yeah, yeah, that helps. That helps because then you
Okay.
think of hidden states, you think of, okay, there's just some underlying information in there, right? That's what you think of when you say hidden states. So like it may or may not be like what you would use in RAG. Um, yeah, that may make some sense. Yeah.
Okay.
Maybe that embedding is using two. It's got sort of an overloaded meaning.
Mhm. And so usually like we call them embeddings because people talk about embeddings with RAG, right? But this thing is like the hidden state output of your LLM.
Yeah, yeah,
Well, of the body of the LLM before
right.
it gets to that. Okay. So this part here, this output, that is the thing that we like that output, you can collapse it down, you cannot collapse it down, and that is the thing that goes into the vector store.
From an LLM, you're saying? Something like a BERT that
Yes.
could go into an okay.
Yes. So that is like when that's the thing that you put into the vector store.
So I'm thinking of like, let's say you do that for like all these vocabulary words, like a corpus of words from like BERT, and each like let's just say we look at all these like words that connotate, women versus men, right? So like or boys versus girls. So like um in RAG, and then you want to say, okay, well, I have these embeddings and I put that into a vector database, you said, right? Or we
Yes.
could. And
Hmm.
then I want to say, hey, what are the closest words to um uh let's- policeman as opposed to policewoman, let's just say. So what are the closest words to policeman?
Hmm.
Um and would you do like cosine similarity in that case? Because that's where I get confused. It gets to my first question of like, well, all these vectors are in some multi-dimensional space.
Hmm.
They're not on a unit circle.
Hmm.
That's how they were represented in BERT,
Hmm.
right? So how does it know to like if we're now trying to do cosine similarity, it seems like we're like comparing apples to oranges to some extent. Like, or does it all just end up mapping down to a unit circle and it all
So it just depends, right? So right now, today, if you wanted to, you could, I mean, you said that you've done this. You could go to BERT and get out the embeddings, right?
yeah, yeah.
You could also, if they come out of BERT unnormalized, you could normalize them. And then you could do cosine
Uh,
similar. You see what I'm saying? Like,
oh,
just how
okay,
you
okay,
treat them.
okay. Yeah, you normalize them. Okay. And do you lose anything by normalizing them? I mean, you lose something, I guess, but maybe it's not, maybe you still, that makes, you may not lose enough. So you may still be able to get a lot of the meaning.
Hmm.
Okay. Because yeah, I've been teaching this to kids. Like my son was taking linear algebra, and so like I presented it to Word to Vec to their class in high school, and I was trying to show them this king man
Hmm.
queen woman thing, and they got it, but it was easy because I could show them that the difference between king and queen was the same as was of the vector of king minus queen was the same as man minus woman, right? That was graphically appealing, but if I tried to do cosine similarity, it wouldn't make sense to them because then all of a sudden you're talking about, well, maybe I would have to normalize it, and that would, yeah, maybe if I did normalize it, maybe it would still show the same similar. They would get the similar vibe. But it was very easy to just look at just pull the word to vec embeddings and and plot those four words and show that. In fact, I did it with like princess, prince, boy, girl, and the I put them all on the same graph, and the distance between the male and female version were almost identical. The
Hmm.
the vector difference, right? But on the unit circle, I don't know how that would be visualized. So that's why I kind of am getting into a rabbit hole, I guess, about that. But I thought that they got that. So at any rate,
I mean, you could just visualize it as the angle between these words. And so for some of them, the angle is like nothing. And so they're sitting right on top of each other because they're like similar. And then for others,
hmm
maybe the angle is larger because it's not. Or maybe it's even perpendicular. No, it's not going to be perpendicular, but it's going to be significant, like different.
So maybe
Yeah, so like,
like that's the visualization that helps.
yeah, I wonder, maybe I'll try that. I'll try to see if I was to convert, if normalize all of them, all those Word2Vec embeddings, and then do a search that way. If we would notice like they all have the same angle. All the female components have the same angle, and all the male components have the same angle. That's what would show up.
So let me think about that. That's so interesting. Also, people do use the embeddings for something a little bit different, which is like if you want to quote unquote freeze the like if you're wanting to build a model that does like classification for like for something, for example, and then you're like you want to like train a model to do this, you can freeze the encoder part, so this BERT part of a model, and
Mm-hmm.
then add a classifier like at the end, and you can like connect it in there, like the real thing. You can connect like a classification head into it, or you could just use the embeddings that are just going to come out of BERT because that's what would come out of it anyways, and then just have a separate classifier that does the classification and train that classifier. So a lot of people will choose to use like the embeddings that come out of like a model and then train a different kind of more like scikit-learn sort of model, which would also be a logistic like model, logistic regression or whatever for classification. Like you get the embeddings first and then you do the training on the embeddings rather than make one big thing where you freeze half of the weights, meaning that they don't change, so you would still get the same embeddings out of that, but then you're training like this whole thing. So that is another way that people use embeddings. So they don't have to like run like this big like transformer model and then train the whole thing, even though you're freezing part of the weights.
It sounded, I mean, I didn't get it because it sounded like they were this, what you were describing was the same in one sense that they're freezing, in one sense they're freezing the weights, or they're freezing only part of the model. Is that the first case?
So let's say that you're trying to train one big model. It's BERT,
Mm-hmm.
and then it's a classifier, and it's a like it's
Yeah.
literally like a logistic classifier, right?
Yeah. Yeah.
All into one big model and train that whole thing. You could also take that BERT part and freeze the weights so you train none of that. And so most of
Mm-hmm.
you training the weights on the classifier.
Yeah.
So this situation where you're freezing that BERT part and training the weights of the classifier is the same as if you were to like take BERT as it was, generate all the embeddings that you wanted to begin with, and then just use all of that pre-computed to train your logistic regression. So it will be just like
Mm.
a tad bit different because you would be training the neural network like with gradient descent and all that great stuff, but like the behavior, the expectation of that behavior is like the same.
Mm. Okay. It's sort of like it seems like it's like, oh, you're taking these outputs, these embeddings of BERT, the last layer, second to last layer, and you're fine tuning them. It seems like with your training to fine tune them to get whatever data you're using to train this classifier, maybe.
You're using the outputs of BERT to train the classifier to do the classification. Does that make sense?
Oh, yeah, yeah.
It
Okay.
becomes like the training data.
Interesting. Okay. Okay.
Let me see real quick if I can dig you up. There's like a really good reference on like it's not a really good reference, but it's just a good reference.
Another way embeddings are being used. So my fiance is getting her PhD at UVA in quantitative psychology, and
Mm-hmm.
they're basically using embeddings, OpenAI embeddings. Essentially, the idea is item generation for psychological tests. And so you get something like a chat GPT or any model really to generate items on a psychological test. For example, it was like the Big Five personality test, where you've generated items for conscientiousness, openness, extroversion, and all those five, whatever they are. They're using a technique called exploratory graph analysis, which her advisor Med did, where they look at the embeddings from the OpenAI model and then use those to cluster similar embeddings together. So, take, you know, all all of those generated items and cluster conscientiousness together and openness together. And that's working really well. And then further using, embedding math to figure out, which one of these conscientiousness items are good and which of them are bad based on literally, I don't know the exact thing, but like distance and cosine similarity combination. That all happens in exploratory graph analysis. But that's one very interesting way. They're just taking these OpenAI embeddings, using them to just cluster and then further examine
Yeah.
clusters to, drop bad items and keep good items. And that actually worked really well.
What's the lab there? I'd love to read some of the papers.
It's Hudson Golino's lab. He came up with exploratory graph analysis a while ago, but Lara, my fiance, has kind of put that with sort of LLMs and is using that to kind of come up with a sort of relatively automated item generation task, which otherwise can be pretty difficult because, you sit there, you get an LLM to generate, 1,000 items on this test, but then now you need 4 or 5 domain experts to sit there, parse through these thousands of items, and then figure out what's good and bad. And that's just really difficult to do when there's so many items. So this kind of automates the initial process of, eliminate the bad items, however you consider them to be bad by whatever metric they're using, and keep the good ones, and then take a look at that final list and then hand this much more palatable, smaller list to domain experts for testing, which
Hmm,
is very interesting use of embeddings.
definitely. Definitely. Wow. This is cool stuff.
Yeah, I don't really understand most of it.
My mom is a psychologist, so she's been talking about, I mean, it's not graph theory by any means, but cognitive behavior therapy and executive functioning for decades, and it's all the rage now. I mean, it's nothing to do with what we're talking about, but if she was younger, she'd probably get into this stuff. But now she's 80, so
And
wow.
here is an interesting reference. Am I saying the right thing? Yeah. And I might have said something crazy earlier. You definitely need the magnitude. Yeah, I think
Oh,
the
this is great. This is
advantage of the
perfect.
dot
Yeah.
product is very much about not calculating, yeah, the magnitudes. I think people do use, I'm trying to remember which one I've seen in documentation because there was a really interesting day that we were going through like all of this documentation on somebody's implementation of their vector store. And we somehow discovered that they were using like a really unexpected similarity measure. We're like, why would they do that?
Hmm.
But I think it was the dot product.
Hmm. Yeah.
Yeah, because yeah, go ahead, sorry.
Yeah, that's what I just like. Because a lot of these slides I used LangChain documentation, and they said, yeah, we've seen dot product be used before, but nobody tends to use Euclidean distance, and they didn't elaborate on that. So I'm definitely going to be reading a bunch on it. But
Yeah, it seems to me if we're using cosine similarity, basically every embedding is effectively on the unit circle.
Mhm.
And that's kind of what they don't seem to talk about that. And I'm like, okay, well, sheesh, if I've got all these words or all these documents or all these embeddings on a unit circle, we're talking about needing a very precise angle measurement. We're really down to 1 degree of freedom here. And so like to really grab similarity, similarity uh chunks or whatever, similar chunks, seems like
so
you're down to this 1 degree of freedom. So
yeah, I think one thing also to think about is the way that these embedding models are trained. I
Mm.
think they're optimized so that sentences with similar meanings sort of point in the same direction. Not, I think like in the training, magnitude tends to matter a little bit less.
Oh, okay.
So some of that is coming from how these models are trained, a little bit.
Yeah, they otherwise, if they weren't trained that way, then that would be quite concerning, I think.
Yeah, and also I think, when you're working with 1500 plus dimensions, absolute distances kind of tend to concentrate because everything will kind of become equally far away from each other. But angular separation in that many dimensions seems to be more informative.
Yeah, you know what? That's what I'm probably over like if you have a 1500 dimensional sphere, there's a lot more space, a lot more differential opportunities before than say in a unit circle. So there's enough space for chunks to still have some differentiation and um yeah, okay. That actually is very helpful to for me to understand. Okay. Well, thanks guys. I know I always keep you late.
It's okay. Keep
See.
it
I love these questions. They make me really think about this stuff
straight.
in ways that I have not.
Okay, I don't know. Yeah, it's just the very it helps me understand it. Once I get the nitty gritty down, then I can kind of move on. It's sort of become a problem for me in this era where everything's changing by the day because I really feel like I still have to know the the underlying principles because it's served me well in the past. Is once I understand how like was a derivatives trader, so once I was like the hedge fund trader, once I understood how the underlying options worked, like how the pieces put together, then I could figure out the nonlinear um create a trade that gave me the nonlinearity that I wanted. If that made sense. But I had to understand how I wanted to deconstruct the individual parts. And so that would give me a lot of edge, I think. But it was time consuming, but it paid off. But now in this day and age, it's like things are moving too fast. Like I'm just trying this whole weekend I spent trying to learn OpenAI SDK, the agents SDK, and like
Yes.
my friend texted me two new ones that just came out. Like I think Amazon literally just announced one
Yes.
today. So
Yes.
like it's
Yes.
like I literally spent the whole weekend just to figure this one out, and I don't know what I'm gonna do. I mean, just gonna pick one and go for it, I
Yeah,
guess.
pretty much. Pretty
So
much. And then with Amazon's one, like, I don't know. I can't wait to check that one out, it seems, because it has like that natural integration, obviously, with AWS, right? So that's really helpful. But there are others that are also really good. And well, I will talk about some of them next week. But
oh, okay.
yeah, it's like once you kind of learn like the general ideas around them, it does just sort of help to be able to navigate between one and the other as to why would you
Mm-hmm.
want the other.
Yeah.
Yeah, also you got to try them because I know that in my class we were trying like these different agent platforms and some were just so good in some ways, just clear as day. But boy, the execution was like zero. Like it was so slow. It was unusable. And then for
Did you
other,
find that did you find that with Crew AI? Crew AI is cool, but it takes I mean, just to in just to load it up is very
uh,
painful. I
ah,
don't know. I'm wondering if what you felt about that one.
Crew
It's
is
a it's
Crew
very
is
cool,
it's
but
so cool, but you have to like you have to do a lot to make it be a little bit more speedy because it is
yeah,
not on
it's
its own
very
speedy.
yeah
But it's an excellent, I mean, it's an incredible platform. That's actually my go-to whenever I'm trying to explain like agents to people. And we will actually do
yeah
that next week. So helpful when trying to explain agents.
yeah it is
But
because
the
you
new,
literally just once you have it set, you just have to change those two YAML files,
Mhm.
and you have a lot of flexibility. So
Within the new OpenAI agents API, like it seems like it's really good. And it has a lot of that same like feel to it where you don't,
yeah
it's like with Lang, man, there's just like with some of these implementations, it's so like wordy in the sense that you have to write so much of so much code just to get to like this very basic behavior. And so, I mean, I feel like these other platforms are really sort of helpful in abstracting away from some of those things. But then in the end, it seems like most people are just like, and after I implemented this and made sure that it was working in crew, then I went to LangGraph and actually implemented it.
So, but I haven't used LangChain and LangGraph at all. But is that one where you say it's kind of wordy,
Yes.
verbose? Yeah. Okay. Yeah, that's what I felt, and I'm not totally sure what I gained from it. Simplistically, like it seems like, okay, well, there's obviously some helper functions here involved, but like I just feel like I'm pretty much creating the entire architecture and using some of their cool functions to make it a little bit faster.
With
I
LangGraph?
haven't with LangChain, um, but I haven't used it properly.
It is when you want pretty much control over everything, all parts, each piece, each nuance, all of it.
Okay.
Yeah, I will say LangChain used to be way more straightforward, and now it's a bit of a nightmare because my last entire year of projects, I've been ignoring version 0.3 and using version 0.2. Don't use anything else. And now I realize I should probably not teach something old, so I spent the weekend teaching myself version 3, and my God, everything has changed.
I'm doing a lot.
Oh, it has. It has. Okay.
Doing a lot.
But it's
LangGraph
good. I like it. It's
doing a lot.
So now that you've done it, you're okay with it, you're saying?
yeah, I
Okay.
think it comes with like just the basic implementations are a little bit more complex now just because it the way you implement even the most basic things keep the door open to doing more complex things now, which initially would have been a little bit more challenging. You have to go back and change things. But now like you change one class and suddenly your bot has memory. You change one more class, suddenly your bot has RAG. So
Oh, really?
it
Okay.
it's hard to kind of jumpstart, harder to jumpstart, but once you have the basics, it's very relatively easy to, monitor, maintain, and upgrade.
Okay.
We'll go over the notebook on Wednesday. That's primarily all I'm planning on doing. Intro to LangChain, putting together a RAG bot with memory, and then putting it all together, wrapping it in a UI, and then you have your LangChain RAG bot in 2 hours.
So for all of these, do you have to use Pydantic pretty much to like create those class functions and whatnot? Do you guys use that? Like I didn't I kind of that's another thing I learned over the last couple of weeks. It's very helpful because it forces the basically doesn't it like I see it as it forces the LLM's response to be in a format that you can is more predictable.
I love Pydantic. I think it's the best thing ever. Honestly, like we sometimes, in university in computer science, we get in these discussions about what we should teach and what's the most important. And the conversation always comes up that you can't really do very robust typing with Python. And I'm like, well, we teach Python with Pydantic, we're back to like very intensely typed like sorts of languages. Anyways, but yeah, Pydantic is, I mean, I think Pydantic is the best whenever you need to, it's just exactly what you said, like when you want specific kinds of inputs or outputs out of your LLM and you want to constrain it to be certain things.
Yeah, and that seems to be like it doesn't stop hallucinations, but at least it allows you to play around with the output in a more controlled manner.
Mhm.
Does LangChain just do Pydantic under the hood?
Oh, it makes sense.
I think that because I in my notebook I'm not explicitly using that anywhere, but it's just like it would make sense that you're using all of that.
Yeah, I mean, I think for a lot of ages, I mean, it really just sits sort of at the input or like output. And it's not really, it would be like how we used to have like what, like the output parsers, like
Mm.
that, like
Mm-hmm.
that would be where you would like want to have like your Pydantic class.
Yeah.
I can if you're up for it, I can show you what I did this weekend.
Let's see it. I'd love to.
I will see if I can I share? The problem is this is on my work computer, so I may not be able to run it because it's on all the files are my local. So this is how amateurish I'm about this stuff. I don't even know how to like this is my GitHub page, but now I have to go and fit it to my work computer and use it. Somehow I've got to get the GitHub repo to my cursor on my computer, and I don't even know how to do that yet. I'm sure you could teach me in one line, but so this is just created a rubric for job descriptions, like,
Yes.
and so um,
Yes.
one of our first companies that we're trying to work with is and all of this was done with like I had one long file of like 1200 code, 1200 lines. And once I finally got it working, I said, okay, this is unwieldy. So I asked Claude to give me a breakdown of how to put this into what's an organized fashion to put it in my GitHub repo. So it came up with this. So this is what my GitHub repo looks like. And it came up with this README file, so it's perfect. So
Nice.
like that was that. And then I wonder if I could do this. How would I do this where I can just take this and put it on my cursor on my computer? Let's see here.
Like from
I can
GitHub?
from GitHub. How do I pull it?
So you would just open a new project on Cursor and then just say clone repository.
Okay, so if I go to open
Let's see.
You might just be able to hit like new window.
Right, yeah. Wow, it looks so
new
different.
window, yeah,
Clone
open
Yeah,
repo.
clone repo right
project.
there.
Oh, clone repo.
Oh, cancel clone repo. Okay. Hello. It's not nothing's happening.
Oh, that's weird.
Yeah, that is weird.
Does it take a while?
It will pop up a little tab on the top of your screen maybe when you hit clone repo. And I don't know if that's maybe like hidden by your Zoom bar or something.
Could it be that we have like an extension?
Oh, maybe.
Because yeah,
I'm
you just
on I'm on the paid plan, I think. I'm on the pro plan.
Let me see if I have any extensions. I
I
mean, you could
should
also
be.
just always do a git clone. I mean, that's also
Yeah, that's what I could also do that. So like if I go to
I would just open up a new terminal at the bottom. Um, yeah. And then just yeah, change directory to wherever you want to go and you could just do a git clone.
okay, so I could do let's see
Here.
mkdir.
if you want to.
Yeah, you don't have to. Yeah.
Oh,
Yeah, okay,
okay.
so you probably don't want to do that.
Okay.
Because when it closes it, it's gonna have that if that's the name of your repository, like it clones that whole folder. So you'll have something called
Oh, okay.
Yeah.
So then if I do git clone,
Yeah, and then go back to your repository. And then yeah, hit that. Perfect. And it depends on how you've set up your like GitHub cloning, if it's HTTPS or SSH.
I'm not sure, but we'll find out. And then so do I do anything here? Just
Paste it in. And
I
it'll
don't have
ask.
to put any letters or anything, any dashes or anything, like dash M or dash R or whatever.
Nope. Okay. Oh.
Ooh, PowerShell.
Oh yeah.
The Windows thing, I have no idea what to do anymore.
Oh,
Maybe
okay.
that's why it's fighting you. Maybe that's why
I'll
it's
just
fighting.
put it in Claude.
I think that you have you ever tried to clone anything before on this computer?
No. Oh yeah, you know what? Maybe I don't have permission. It's my work computer.
Do you have like Git Bash installed on this computer? Does that sound familiar?
No.
Wait. What is command prompt?
Ooh.
Do you
Uh,
have Click this one, this command. Oh, that's still going to be PowerShell-y.
Yeah.
You could, you can try it with a, I feel like I don't think we have an extension.
I'll just see. Claude will give me a solution pretty quickly, I think.
Yeah. Maybe it's like the Mac thing, because like by default, we can type in like git clone, and if we don't have git installed, it'll be like, you should install da 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 da, and then you install it, and then you type git clone again, and then it works.
You just need
I
command.
may, yeah, it may very well be that I do not have GitHub on my work computer.
Oh, you could always install like yeah, you could install, what is it called? GitHub desktop.
Oh
Yeah,
yeah.
yeah.
But it really should be that you should, man, I'm trying to think if I've seen any Windows people just go and click clone repo. I feel like yes, right?
I think so.
I think once I do it on my laptop, which is a Windows. I think I've just downloaded the GitHub on there. So
When you get back to your laptop, try to click that clone repo button and see if it works. Because yeah, that's like the best. It's the best.
I'm gonna see. I'm gonna install it here. Let's see if they'll let me, or if I'll get if the company has stopped me from installing it. Seems to be installing. But that's where, yeah, I would never be able to do this without AI, obviously. Because it took me all weekend with AI to get this far, but it's amazing. It's just, I mean, you guys must have a lot of discussions on the state. Abby, you're doing all the work on AI in education. So like, it's going to be just such a huge change for the education field.
Yeah. Yeah, I mean, I think a lot of discussions happen at Vanderbilt too about how classes are going to be taught. I mean, I think, yeah, pre-K all the way up. It's a big,
Yeah, yeah.
yeah.
It's installing. I'm glad they didn't block me.
Which one is it? Is it GitHub
Oh,
desktop?
it says GitHub launch GitHub bash. So here's GitHub.
Oh yeah. This is Git bash.
Okay. So I wonder now if it's actually installed, I can use it on Cursor.
That's interesting.
No.
Well,
didn't
so
work.
this particular shell that you're looking at is yeah, you might have to like maybe like restart it or something because maybe it hasn't like seen it, but that one is still PowerShell.
Okay.
But did you like see I can't, I don't know. I've never tried it, but like maybe it just needs to see. Oh, I forgot when you close things, they really close. Yeah, I forgot about that.
Okay, so now this works. So clone from GitHub. It
Yay!
showed up. The clone.
Yay.
Allow extension. Where does this show up on my? Enter the code displayed on your device.
It should already be copied to your clipboard.
Oh, okay. Oh, cool. What is this?
Boy, they'll have you authentic. Oh my gosh, the students made fun of me one day because I had GitHub Mobile, and I was like, "Oh, give me a second, like." I have to authenticate on GitHub Mobile, and they were like, "You have GitHub on your phone?" And I was like,
Yeah.
"Yes."
Doesn't everyone?
I'm like merging in pull requests on my phone.
Me too. Me too. I was like, I can't believe I'm the laughing stock of this conversation.
So I don't know what happened here, but oh, here, let's see if this works. No.
Yeah, just the first one, and then you can give it a location to clone. Yeah, so this
Oh, okay, got it.
Isn't that nice? There's no more CD. It's just like, I got you. Oh,
Device authentication. It's asking for device authentication.
and Git Bash maybe? Oh, again. Oh, there it goes. Yeah. Do you have more than one Git account on your device?
No, I have multiple emails on that on the account, but
Yay!
uh,
Yay!
okay, cool. Thanks, guys.
yeah.
Enjoy.
So
Enjoy.
then if I do created this thing here. So if I do oh, I guess I have to still create do I have to create a new it doesn't come the venv doesn't come with it?
Did you have one in the GitHub
Huh.
repository?
Oh, you know what? I probably was ignored, I'm guessing.
At least you have the requirements.
Yeah.
Yeah, so I can do
Yay!
well, that's fast. So then if I do hi one, oh, come on. Oh, do I not have I don't have my end file in here. Okay. Fix that.